IFIMAC+ICMM Series. Thanks for joining us. Today, it's my pleasure to introduce Victor Pardo from the University of Santiago de Compostela. Victor finished his PhD in 2006, studying the electronic structure of cobalt oxides, and then spent 4 years at the University of California, Davis as a postdoc. Since 2012, he's back in Santiago de Compostela, first as a Ramon y Cajal fellow, and since 2017 as an associate professor. Victor is an expert on first principles calculations of the electronic structure of materials, in particular complex oxides, magnets, superconductors, thermoelectrics, or topological systems. More recently, he has also studied nanostructures of such systems and low-dimensional materials as novel 2D ferromagnets. Today, Victor is going to tell us about his work on nickelates, a material that he already studied more than 10 years ago and has been recently found to be superconducting. If you have any questions during the talk, please ask them in the chat and I will read them to Victor. At the end of the talk, we will open the mics for everyone and you will be able to ask yourselves. Well, Victor, thanks for coming. The screen is yours.
Thank you, Maria Jose, for the kind introduction. As you said, I'm going to tell you, try to guide you through a journey that we've been covering for the last 11 years already. I started getting interested in this layered nickelates when I was a postdoc at Warren Pickett's group in UC Davis, and through these years we've learned a lot with our colleagues. I'd like to mention John Mitchell here. He's been a driving force person that has pushed us all to understand more and more nickelates, more properties. He's provided us with great experiments that we could compare with. I've also collaborated a lot with Antia Botana. She's a professor at the Arizona State University now, where she and her PhD students, we've been working on these nickelates for the last few years as well. In my group in Santiago, Adolfo Terofumega has also participated in this project, and we've also collaborated with Dan Dessau from Boulder, Colorado, and his students there. So this is just some of the people that we've worked with in the last few years, and I will mention explicitly some of the collaborations that we had. So what I will present mostly, like Maria Jose said, I basically do electronic structure calculations of different materials. I will present mostly DFT calculations in this presentation. I will talk about a huge variety of these layered nickelates, and mainly for the experts in the audience, I will tell you that we've introduced correlations basically in a static way with the LDA plus U method. We've tried to compare with all sorts of experiments, and all the different structures, the relaxations that I will discuss are calculated without correlations at the LDA or GGA level. Okay, so this is the outline of the talk. So I will try to cover what I know about layered nickelates and why they are interesting. Mainly the motivation for understanding nickelates is that they are very similar to the cuprates. So I will discuss a bit what our journey has been trying to find cuprate analogs and why. And I will discuss why these nickelates, in particular this one, is a bit different than the cuprates. And then I will go through why we believe we not only have a superconductor candidate, that we have a whole family of nickelates that are worth studying. So it's not only this lanthanum nickel O2 that has been found superconducting, but there's a whole family of nickelates that maybe they are not superconductors, but they are worth being studied, because if they are not superconductors, then they will teach us something about the physics, not only of nickelates, but of cuprates as well. And I will try to tell you why this is, and finish with some remarks. So this is the motivation. The motivation is trying to find systems that are similar to the cuprates. The cuprates are the materials with the highest transition temperature, superconducting transition temperature that we know. So it would be very interesting to find other materials that share similar properties. So I will mention a few of the properties of the cuprates that we're interested in. First of all, the cuprates appear in different families, different structural families that we have here, but they share some common features. The most important one is the quasi two-dimensional structure with these copper O2 planes. In those copper O2 planes, we have, in the undoped compound, say, we have copper 2+ cations. This has 9 electrons in the D shell. So it's one hole in an x squared minus y squared band. And that x squared minus y squared band basically couples antiferromagnetically in the plane. So then the parent compound is an antiferromagnetic insulator in 2 dimensions. And this is common for all the cuprates. The occupation of this single band occurs because of this Janthaller's distortion that I am depicting here. When you have an octahedral environment of the copper cation, you have this level splitting of the D levels, and when you stretch a lot the octahedron, or even when you remove the apical oxygens, what you have is that these x squared minus y squared orbitals that are pointing from the cation to the anions are highly repelled, and they appear basically at the Fermi level, very separated from the rest. So what one would like to understand is what other systems share some of these features and whether they are superconductors or not. This is more or less the phase diagram of the cuprates. As I said, you have the antiferromagnetic insulating phase at nominal D9 filling, and when you start doping it, when you start changing the electron count in the D band, you have a superconducting dome with a very high transition temperature. And here at this limit, you start having a more normal metal, maybe a Fermi liquid or maybe a strange metal, but certainly a metal. So I will refer in different parts of the talks to this point here as an antiferromagnetic insulator and this point here as a metal, as 2 good reference points where we can make calculations in layered nickelates to actually compare with the cuprates. So as I said, the question is, do we have this similar phase diagram? Do we have this similar electron structure in other materials? Well, we've had different proposals through the years. One of them was by particular Thomas Sentil with these iridates. And he said that maybe in these iridates, you could have the same physics as we find in the cuprates. So these are quasi two-dimensional materials with an iridium 4+. This iridium 4+ forms a square lattice with antiferromagnetic in-plane coupling, just like the cuprates. And it is very similar to the cuprates because it has one hole in the T2G manifold. So there's more or less an octahedral environment. You have 6 electrons here, 4 electrons up there. These are unoccupied, and this will be occupied. And there will be one hole here. Because the T2G manifold works as an L=1 subsystem, when you introduce a spin-orbit coupling and iridium suffers a strong spin-orbit coupling, you have L+½ L-1/2 manifolds, and you have one hole here in a J-effective 1/2 orbital. And this is similar to the spin-1/2 of the cuprates. So in principle, similar physics could be expected in these nickelates. The problem to find it experimentally is that these iridates are difficult to dope. So what people have done is surface experiments, and in surface experiments, they can sprinkle some dopants on the surface, and they do measure a D-wave gap with STM or other techniques. They do measure something which could resemble the physics of the cuprates with the same symmetry, but they don't have the smoking gun experiments saying, say, zero resistance typical of superconductors, because these are very difficult to dope in the bulk. But certainly this points in the direction that, okay, maybe other systems similar to the cuprates can be found. Another not so successful possibility was proposed by Chelupka and Helyulin a few years ago. They said it's okay, instead of having one hole in the EG states, we can have one electron. This can be attained with, for example, lanthanum nickel O3. This is a 3+ nickel 3+ system. It has one electron in the EG levels. And what they said is, okay, we can grow lanthanum nickel O3 in thin films, and with a substrate, we can strain this octahedron, we can enlarge it or compress it so that the EG levels become shifted in energy. The situation would be something like this. They can try to create artificially with strain something similar to the Jan-Teller distortion that naturally appears in the cuprates. So they say, okay, we can split these bands via strain and get a single band picture similar to that of the cuprates, but instead with one hole, just with one electron. However, when you go to experiments, the actual strains that you can introduce with typical substrates like LAO is very small. It is very small. And what you see from calculations, for example, this one from Philip Hansman, is that if you look at the band structure, yes, the bands are somewhat split, but the bandwidths are very large, and you never get a large orbital polarization. You never get that around the Fermi level. You have a single band picture like in the cuprates. So this one is not a good example to pursue. One possibly better way would be to go to lanthanum nickel O2. And this has been considered for more than 20 years already. Anisimov was one of the first in doing calculations in lanthanum nickel O2. Lanthanum nickel O2 would be nickel plus, would be the exact same nominal filling of the d band as in the cuprates. They are next to each other in the periodic table, so copper 2 plus has the same number of electrons than nickel plus. But this system is metallic. It's not like the parent cuprates that are insulators. This lanthanum nickel O2 parent system is metallic. So more people got interested in this, and Warren Pickett already in 2004 said, okay, well, nickel plus is not copper 2 plus. If you have the parent compound of these nickelates, it's not an antiferromagnetic insulator. It has these hugely dispersive bands that cross the Fermi level. So the system is metallic and paramagnetic. And people realized really soon that also in these nickelates, the oxygen p bands are farther away from the Fermi level than in the cuprates. You can see actual calculations more recent by Antia Botan and Mike Norman. What they calculated was the on-site energies of the d bands and the p bands. And in the cuprates, they are in the same energy range. But in the nickelates, this is not the case. In the nickelates, the oxygen p bands are much lower in energy. So this involvement of the oxygen p bands around the Fermi level that leads to interesting physics in the cuprates is not present in the parent compound of these nickelates in lanthanum nickel O2. So in principle, well, maybe nickel plus is not copper 2 plus. Other possibilities that we've considered through the years, I'm trying to guide you in more or less in a historic view of how we've come to understand all these nickelates. About 10 or 12 years ago, two groups in the US, this was Martha Greenblatt's group and Takeshi Egami's group, they produced these samples. These are related to the Brothers and Popper series of these oxides, this lanthanum 3 nickel 206, lanthanum 4 nickel 308, and these have increasing valences. They have increasing filling of the nominal d band, reduced valence towards nickel plus. Nickel plus is really difficult to synthesize. It's not like copper 2 plus. Copper 2 plus is a very happy cation that you can synthesize lots and lots of materials with it. Nickel plus is difficult to attain, and these are samples that are not easy to make. So reaching the nickel plus oxidation state is not easy. So these samples they could do with reduced valence. So they share this structural motif, this nickel O2 planes, square lattice, similar to that of the cuprates, but they appear in bunches like this n equals 3 has 1, 2, 3 layers here, which is separated from the other 3 by a fluoride slab. And in the n equals 2, you have 2 layers here of nickel O2 that is separated by this fluoride slab from the other 2. So these are interesting, certainly very similar to the cuprates, and with a feeling that is getting close to the interesting part of the phase diagram of the cuprates. So they produce them in this way. They create first the Rudolph Popper, and then they remove the apical oxygens. So basically what you get rid of is of these apical oxygens here. So you get the square planar environment around the nickel, this hugely Jan-Teller distorted environment that leads to the splitting of the EG bands as we had in the cuprates. Yeah, but these samples, they are not very clean. They even have nickel metal inclusions. The grains are really huge. The intergrains are really huge. So these samples are not very clean because they are difficult to make. It's normal. So So we even started, remember we come from this Rutherford and Popper, we first started one of those without removing the oxygens, and we found interesting physics here. You can see that when you measure with ARPES, which is what Dan Dessau did with his group in Boulder, what you see with the Fermi surfaces of these 4-3-10 is that you see, well, this like in the cuprates, you have these sheets of the Fermi level. You find them in the measurements that they did, but you have additional bands. You have many additional bands, which are basically dc squared in character. These are the dx squared minus y squared of the cuprates, and you have those similar Fermi surfaces plus many additional features, because you are far from the feeling that is interesting to compare it with the cuprates. But you do see some parts of the Fermi surface that resembles the physics of the cuprates. This work is somewhat interesting for us doing DFT calculations, because we could compare what are DFT predictions, how good they were compared to actual measurements of the band structures of the extracted from ARPES. And the calculations saw that the bands calculated are very good when compared to experiments, and you even have some mass enhancements that you can compare here. So for people doing calculations of correlations, this is a good indication of what the typical mass enhancements you would find in these nickelates. Something else that we saw was that some of these nickelates have charge density wave transitions. You can see it here in the resistivity of this material, that it has this kink at 100 and something Kelvin, and you can trace it to the behavior of certain bands. You open these gaps. You have this typical charge density wave transition associated to opening of gaps at certain K points of the Fermi surface and related to certain bands. And what we could see by comparing ARPES and DFT calculations is that this is related to these C-square bands. And this is interesting because those C-square bands are the ones that you want to get rid of if you want to move to the physics of the cuprates. So if indeed we get rid of these C-squared bands and put them away from the Fermi level in these nickelates, we could also get rid of these charge density waves that some of these nickelates have and that don't seem to be good for superconductivity. So one additional problem we have with these samples, as I said before, for example, with this 438, once the oxygen is removed, is that they are very dirty. So when you look at the resistivity is huge. You are basically measuring only the grains, but it looks like it is an insulator, and also the 3 to 6 is an insulator. So that's a bad starting point to try to find superconductivity. If you're approaching the region where the superconducting dome should appear, you should be getting a metal that would be interesting for you. But what we see is that these are insulators, and this material, lanthanum 4 nickel 308, has a particular magnetic transition at about 100 Kelvin, pretty unconventional, that is also seen at zero field. So you see here in the specific heat, you see a cusp here at about 100 Kelvin. So something happens to lanthanum 4 nickel 308 at about 100 Kelvin that is related to magnetism, but also maybe to structure. So in order to understand it, we need to add an additional ingredient that we don't have in the cuprates. So in the cuprates, copper 2+ is a low spin state. There's no problem with that. But with the nickelates, when you start filling the EG shell, you can do it in two ways, and this compete in energy. So this is an additional ingredient that you don't have in the cuprates. It could be that the crystal field is big, and you have what is called a low spin state because you start filling up spin, down spin, and then the up spin again. Or it could be that the crystal field is small, and what's big is the Hund's coupling, so that spins want to be parallel, and then you have a high spin state. So depending on the competition between Hund's coupling and crystal field, you could have low spin or high spin solutions. This low spin solution would be interesting because it would have the dx squared minus y squared band at the Fermi level. This would be partly filled, and this would be a metal. However, this high spin state solution, it would have the dc squared electrons at the Fermi level, and this could suffer bonding, antibonding, splitting, and leading to an insulating solution, which is what you don't want if you're looking for superconductors. So we need to understand when these two phases, how they compete. And what we saw, as I said before, when you have the low spin state solution, you have a metal, you have a representation like this. At the Fermi level, you would have a partly filled band, and the big weight at the Fermi level would be the x squared minus y squared electrons, just like in the cuprates. And as I said before, from the data of the resistivity, you didn't know much about the behavior of this material. That's why Goodenough's group, what they did was getting rid of the contribution of the grains by measuring the CVEC, the thermal power. So what they saw is that at low temperatures, it is indeed an insulator, but at high temperatures, it is a metal. And with the CVEC, you see it very well. The CVEC is very low at high temperatures. And even though you see the slope of the resistivity is not that of an insulator, this is because of the grain contribution. So this to us was clear that the high temperature solution is low spin, and at low temperatures you have a transition to an insulating solution. So it's definitely not low spin; it's something else. This we studied it back in 2010 or so. So in 2015, 16 or so, we came across this data from John Mitchell. What he did was he could get single crystals of this lanthanum 4 nickel 308, and what they saw was that with the single crystals they could measure much better the properties, the structural properties of this compound that with the powder that was available 10 years before. And what they saw was that there were additional superlattice peaks at low temperatures. So what was producing the low temperature insulating state was some kind of a reconstruction, of a structural reconstruction. So we said, okay, let's try to calculate some supercells. And what we saw is that there was a particular charge order pattern that was the ground state, that was lowest in energy. And it goes something like this, as you see in this cartoon. Some stripes are formed at low temperature that have nickel plus, which are spin a half, and this a stripe of nickel 2 plus. So this is like kind of a charge order situation that opens a gap. So at low temperature, you don't have the low spin solution. You have a competition between different charge and spin states. This nickel 2 plus is low spin, and this nickel plus are spin a half, like in the cuprates. So our prediction was that this was the structural pattern, but also with the structural pattern there was a charge order and a spin order. So so this was what we predicted, that these stripes would be magnetic in this way. So our colleagues 3 years later, what they did was, okay, let's try to find the spin structure with neutron experiments, and they actually confirmed our prediction. They saw that these stripes had the actual charge and magnetic ordering that we had seen from our calculations, which DFT calculations are pretty good in predicting that kind of structural and magnetic distortions. So okay, so this was what we knew at the time. This was some kind of phase diagram that we put together at the time with our knowledge. At that time, lanthanum nickel O2 was just this ending of this phase diagram that was not coinciding with that of the cuprates, because the cuprates here at this filling of the D band, they are insulators, whereas this lanthanum nickel O2 is a metal. And in this part of the phase diagram, you see here the 3D electron count, the nominal electron count of the D shell. We had this 438 that in terms of electron count were pretty close to the superconducting dome of the cuprates, but we wanted to have a Fermi liquid here, and we have an insulator. or at least an insulator at low temperatures, which is where we are interested. So we needed to do something. If we want to get nickelates that are closer to the cuprates, we had to start with a Fermi liquid here at least, or a metal. So we said, okay, what can we do to turn lanthanum 438 into a metal? Well, what we saw at the time when I was with Warren Pickett in California, what we said was, okay, let's try to pressurize it. We reduce the volume, and we know that by reducing the volume, it is very common in this oxide that the low spin state becomes favored. So at lower volumes, the low spin state becomes favored, and with it, metallicity should appear. So a few months later, Goodenough's group did the same thing with their samples. They pressurized them, and what they saw is that indeed the charge density wave transition goes away, and the system moves to a more metallic situation. They don't reach the actual metallicity because the system undergoes a structural transition, but that's a different story. So okay, when you reduce the volume of this compound, you get something closer to a metal. But pressurizing materials is not that easy to make. So we thought, okay, there has to be some other way to produce a metal, and we substituted lanthanum by praseodymium. Praseodymium is smaller than lanthanum, and well, what we thought was, okay, this would bring about bring the system closer to a metallic solution. And our calculations, what they say about the spin state of the nickel in this structure of the praseodymium 4 nickel 308 is that indeed it is a low spin. So what we did was comparing the energy of the low spin and high spin with two different LDA plus U flavors. This introduces correlations in the D band, in something similar to what you do with the Haber model. And there are different ways that you can introduce correlations. They are called flavors in the LDA plus U method. So we used two of them. And what we saw is that this flavor called AMF gives that the system is low spin for all values of U. In the past, we knew that also for lanthanum 4 nickel 308, this particular flavor of the LDA plus U was giving a better agreement with experiments. And this other flavor, so-called the FLL, which is very commonly used, tends to favor the high spins. And in this case, it at high U's, it does not coincide with experiments. And this is important to know for us doing calculations to be able to make predictions when you don't have experiments available. We have tracked pretty well that this particular flavor of the LDA plus U agrees with experiments in these nickelates. And in this case, our prediction was that this system would be low spin and it would be metallic. And indeed it is. You see the resistivity of the praseodymium 438 is this blue curve here, and it's a metal. And also there is no trace of a charge density wave in the specific heat. So chemical pressure works in producing a metal at this filling. We would be here in the phase diagram of the cuprates with a metal already. So what we saw from our calculations also and from the experiments. The experiments these experiments of the spectroscopy were carried out by John Freeland, and what he saw is that you have a huge orbital polarization. This means that you can measure the spectrum in the AB plane and the spectrum along the Z-axis, and there's a much higher absorption for the orbitals in plane than the orbitals out of plane. And this is similar to what happens in the cuprates. The reason for this, we see it here in the low spin density of states of our calculations, is that you have at the Fermi level and above, you have basically the in-plane orbital, which is this x squared minus y squared. It has a much higher occupation than the dc squared, which is the out-of-plane orbital, and that's why you get this much higher orbital polarization for the in-plane orbitals. And this resembles the physics of the cuprates. So we are in a very good position. We already are here with a nickelate that is a metal. So this would be this praseodymium 438. So we said, okay, well, how can you move it? We need to dope it. We need to dope it and dope it with the correct physics. So we said, okay, you can introduce here a cation that is 4+, so that the electron count would be a nickel plus D9 if you introduce it in, let's say, 1 out of 4. So if you introduce praseodymium 3 cerium nickel 308, that would be the correct electron count for being here. And the idea would be, okay, if you do that, do you get an antiferromagnetic insulator like it happens in the cuprates? If the answer is yes, then you would have, well, at least from this, you know it from experiments, and this end you would know it from calculations. You would be in a good position to at least mimic 2 of the points of the phase diagram of the cuprates. And if you dope it slightly, maybe you can reach superconductivity. So we did the calculations, and with this introducing here the cerium instead of praseodymium, what you end up having is the opening of a gap, and the system wants to be antiferromagnetic in the plane. So this point we know it from experiments, and this point we have calculated it. Whether what happens in between is like in the cuprates, we just don't know. What it seems clear from recent experiments and calculations is that the exchange is the magnetic exchange is indeed large, and it wants to be antiferromagnetic. So our calculations seem to be quite correct. At least the comparisons with experiments are reasonable. So now we come to 2019, and in 2019, this paper by Harold Huang's group appeared, where they finally found superconductivity in one of these nickelates, in particular doping neodymium nickel O2 with strontium. So the reason why they said they introduced neodymium instead of lanthanum in the nickelate is to basically mimic our idea. We had seen that introducing praseodymium instead of lanthanum brings about metallicity because of the smaller size of the praseodymium instead of the lanthanum, and they said that they tried to follow our idea of using neodymium to make it more metallic than lanthanum. And well, they succeeded in getting a superconductor, and this was a great excitement for all of us working in this field for many years already. So let's see what the electronic structure of neodymium nickel O2 is in a bit more detail. So I presented to you in the beginning of the talk some electronic structure data in lanthanum nickel O2 by Warren Pickett and Anisimov, where they were saying that nickel plus is not copper 2+. The reason why they say it is that because in this either neodymium or lanthanum nickel O2, you have these hugely dispersive bands that cross the Fermi level. So this has nothing to do with the prototypical electronic structure of the cuprates with just a single x squared minus y squared band around the Fermi level. No, you have this band that is actually, it has some DC squared parentage mixed with the neodymium F bands. So there's a strong mixing between the nickel and the neodymium or lanthanum bands that produces these hugely dispersive bands. So this produces what is called a self-doping effect. This means that the DC squared band is partly unoccupied, and the rest of the electrons come from the neodymium or lanthanum. So the nominal filling is D9, but there's a different number of D electrons coming from the nickel because of this self-doping effect. But yeah, the structural situation, these nickel O2 planes are just like in the cuprates. So one of the questions that we tried to address first was, okay, we have this neodymium nickel O2, we want to dope it with strontium, and if you dope neodymium nickel O2 with strontium, you move from nickel plus to nickel 2+. And like George Sawatsky pointed out really early, in conventional oxides, nickel 2+ is spin 1. So what is happening here? Are we doping with a spin 1, and does this make it different than the cuprates? Remember that in the cuprates, when you dope, you have these sunrise singlets, you have non-magnetic dopants. So is the situation in nickelates different? Are we doping with a magnetic dopant? So we said, okay, well, let's calculate it. We have to calculate what the energetics of this situation are. So we want to know if you dope with a nickel 2+, whether this is low spin or it is high spin. If it is low spin, then you would have this situation favored, and if it is high spin, then you have this S=1. That is very common in nickelates, but what about when you have a square planar nickelates? Is it the same thing or is it different? And DFT calculations can actually answer this. So what we did was setting up supercells. We have the undoped case. We started with this 2x2 supercell, where one of the neodymiums is substituted by strontium here in blue. We did a 3x3 to mimic something closer to the electron counting in the superconducting, in the materials that were found to be superconductors, where you have one strontium in 9 with 8 neodymiums. And also we did this one, which probably is not the energetically favored situation, but it helps us. We basically clustered 4 strontium atoms here around a certain nickel, and this helps us understand the electronic structure of what would be nominally a nickel 2+ dopant. Here we would be able to see what the density of states is of this nickel 2+ dopant, and that will be interesting, even if in reality the dopants don't want to cluster that way. So what we did for all of these was comparing the high spin and the low spin situation, and again with the AMF flavor of the LDA+U method, the way we introduce correlations for all values of U, always the low spin is favored, always for either lanthanum or neodymium, for the two types of doping. And again, for the other flavor that has this tendency to favor high spin states, yeah, at high U's you have it as favored. But again, our prediction from the calculations and from our experience with other nickelates, knowing that this flavor gives a better agreement with experiments, is that the dopants will be low spin. And if they are low spin, that makes these nickelates closer to the cuprates when doped. The cuprates, when you dope them with non-magnetic dopants. And these nickel 2+ dopants that you introduced, that Harold Huang introduced to create superconductivity, calculations say that they are not magnetic. As I said, with this 4x4 supercell, where we have this 4 strontium here around this particular nickel, this is nominally a nickel 2+, and we can see how the density of states of a nickel 2+ would be in that material. And we see that the stable solution is the low spin, just like in the other supercells that we calculated. And we can look at the density of states for the different orbitals. We see that the difference between the low spin and the high spin is the involvement of the nickel dc². In the high spin solution, which is not stable, you would have a strong appearance of the dc² orbitals at the Fermi level, which is quite contrary to the physics of the cuprates. Whereas in the low spin energetically favored situation, the dc² orbitals are fully occupied, and around the Fermi level you have this single dx² minus y² band that is the one that appears in the cuprates. So it seems that doping brings the system closer to the cuprates. Something else we noticed is that the density states of the oxygen p bands, when you start doping it, remember that I said at the beginning that one big difference between nickelates and cuprates is that in the undoped compound, the oxygen p bands are quite low in energy. They are far away from the Fermi level. But when you dope it, when you start doping with strontium, the oxygen p bands move towards the Fermi level. So this means that when you dope these nickelates, when you dope lanthanum nickel 02 or neodymium nickel 02 with strontium, the physics, the electronic structure, their electronic structure is more similar to that of the cuprates. The charge transfer energy gets reduced, and the system resembles more the cuprates. One more ingredient, the lanthanum bands. The lanthanum bands move higher in energy. That means that when you start doping with strontium, the self-doping effect, this is the partial occupation of the rare earth band, just disappears. The bands move higher away from the Fermi level, and the self-doping effect that occurs in the undoped compound is not happening when you dope it. So this was an ingredient that was making these materials different than the cuprates. So when you dope it, these nickelates become more cuprate-like. Okay, so we know that when we dope them, they become more cuprate-like. But what about this point in the phase diagram? Do we have an antiferromagnetic insulating phase in these nickelates at all? Does it exist at all? Well, the bulk neodymium nickel O2 is paramagnetic and it's metallic. We have these hugely dispersive bands that cross the Fermi level. But what happens if we just grow a single layer of neodymium nickel O2? In that way, you basically kill the off-plane hopping. The off-plane hopping is what is producing these hugely dispersive DC squared bands, which are the ones that are highlighted here in this band structure. And indeed, if you have a single layer of neodymium nickel O2, the DC squared bands become really flat. They cannot hop along the C-axis, and the system is an antiferromagnetic insulator with this checkerboard spin pattern in the plane, just like in the cuprates. So this point in the phase diagram that is characteristic of the cuprates also exists in these nickelates. What you need to introduce is a dimensionality ingredient. You could also study this. This is a toy system, of course. What we did was a 1-1 multi-layer of neodymium sodium O2, neodymium nickel O2. What this does is producing a nickel O2 plane together with a sodium O2 plane, and this kills the off-plane hopping nickel-nickel. But the neodymium would still exist. So if the bands that cross the Fermi level in the bulk compound are produced by neodymium hopping, this would still exist here. But we see that is not the case. When you look at the band structure, the system has a gap. It's an insulator. It's an antiferromagnetic insulator in the plane, and the DC squared bands are non-dispersive, basically. So what you need, what is happening in the bulk in this neodymium nickel O2, you remember these hugely dispersive bands, they occur thanks to the nickel-nickel off-plane hopping along the C-axis. So, well, okay, this is a system that would be it's just a toy model. So, are there any other system where this can be happening? Yeah, certainly so. In the 438, for example, in the higher order nickelates, you would have this naturally because in this case you have 3 layers of nickel O2, but then they are separated by this fluoride slab that blocks the nickel-nickel off-plane hopping. So if you block the nickel-nickel off-plane hopping, what happens is that, again, you look at the band structure and the nickel DC squared bands are contained. Let's say they are not highly dispersive, and you don't have that metallicity in the parent compound. What this calculation of the band structure is neodymium 4, it's lanthanum 4 nickel 308, but with the filling moved to D9, artificially moved to D9. It's similar to what we did with cerium. This is here for comparison. This is just artificially moved the Fermi level to have a D9 filling of the nickel bands. The only difference is that here you have the cerium bands that we introduced in some other way. But the band structure is similar. It's an antiferromagnetic insulator. So you can have pretty naturally with these higher order nickelates the D9 filling antiferromagnetic insulators. That dimensionality factor that is missing in the neodymium nickel O2 bulk. And people are starting to explore this. We of course have no data yet, but people are starting to explore. People have have thought of these higher order nickelates, and they have noticed that, well, okay, this n equals 3 is away from the correct filling, but n equals 4 that can be grown with MBE, or n equals 5 that can be grown by MBE. These people have grown them in the Rutherford Popper. The idea would be, can you remove oxygens from these in order to make them have the correct defilling? Well, we believe that this is a path to pursue, to try to find superconductivity or not. What the calculations say, what Antía Botana, Onur Erten, and their collaborators have seen, is that if you consider a TJ model just for the x squared minus y squared band, the coupling strength, the superconducting coupling strength, would be much larger in this 438 than it is in the 112. So it is worth trying to pursue these compounds, trying to find these samples and see if superconductivity exists in them or not. We will learn a lot just by knowing, even if superconductivity does not appear in them. So with this, I come to my conclusions. I hope I have convinced you that these layered nickelates are very interesting, not only because we have one superconducting compound, because there's a whole family of nickelates that could be superconductors, or maybe they are not, but they will teach us a lot about the physics of cuprates, about the physics of superconductivity, even if they are not superconductors. I have tried to show you that many of these nickelates share a lot of common features with the cuprates, and those who don't have them, when you dope them or when you apply dimensionality, the physics of the cuprates appears. We just need to understand if that will help us in finding new superconductors or not. But I believe this is a really exciting time for studying nickelates. So I thank you for your attention.
Thank you very much, Victor, for this great talk. So now you can unmute yourselves. If you want to make questions, please, you can raise your hand in reactions. So we have, so you can ask questions in order. So so we have a question already. Great, Ilya.
Yes, hi, very nice talk. I actually wanted to ask you, can you discuss, you didn't, I think, discuss it very well in the talk, what is the role of the STO substrate in driving the superconductivity, in your opinion?
In lanthanum nickel O2?
Yes, yes. I mean, you haven't touched it in the talk, but maybe you have an opinion on this.
No, I don't know why STO would be important. I don't see it. I don't see what, apart from sample questions that you need to grow them in a particular way, that you need to grow them with a substrate. But I don't see any electronic structure role of the STO. So I don't see any magic like that happening in the iron selenium, for example, that only grown on top of STO you get something which is really unusual.
But only for monolayer. But then,
right.
Am I correct? Somehow I have a feeling that when you were showing the lanthanum nickel O2 band structure, I guess this was computed for the structural parameters of the bulk. How this band structure would change if you do it on the STO? Because somehow I understand that the lattice parameter, if you grow it on the STO, is a bit different. And my impression, I mean, again, I did not put two pictures next to each other, but somehow I had the feeling that they are not identical to some extent, especially with respect to the x square minus y square band. Somehow it looks like it becomes more flat. Is the lattice constant in the plane also extends? I mean,
So there are some changes. I saw a paper recently that discusses all the series of the lanthanides, and that there are some trends that you can understand, but the essential physics, the essential electronic structure is not changed. I mean, you can have some differences in the position of the bands, in the bandwidth, certainly, that will give you some second order effects, but there is no trace, no indication that the substrate effect, that the strain effect would be the driving force, would be the driving role towards superconductivity. There is no indication of that.
Okay, thank you very much. Yeah.
Okay, Lenny, can you please?
Hi. Thanks for the great talk. There is something that I'm not 100% sure if you have mentioned, but you have said that the monolayer and the nickel O2 can be similar to the parent compound of the cuprates, and in particular that it can be an antiferromagnet. Is similar to the cuprates just in being antiferromagnet. Do you know anything on whether it is expected to be charge transfer insulator, something like motor, just simply
so it is
another kind of antiferromagnet, like a later insulator, something like. So do you have any information on that?
Yeah, I mean, certainly the oxygen p bands would be much farther away from the Fermi level than in the cuprates. Yeah, so we know that. But the thing is that it's crucially different to the bulk, so the main idea of that calculation is that the antiferromagnetic insulating phase of the nickelates exists. You just need to add an additional ingredient, and that helps you understand where that hugely dispersive band comes from, because there's some discussion as if that band is really neodymium, is it really nickel? So what we see from those calculations, which are really toy models, is that what brings about the hugely dispersive band is the nickel DC squared continuity along the c-axis that exists in the neodymium nickel O2. But then when you try to compare that solution that we get with the cuprates, certainly the oxygen p bands are much lower in energy by 2 or 3 electron volts, and that was calculated by Antia Botana and Mike Norman. And it is similar in the monolayer. To bring those oxygen p bands closer to the Fermi level, you need to dope it. When you dope neodymium nickel O2, you move those bands closer to the Fermi level. But going to the monolayer, you don't do that. You just get rid of the DC square band, basically.
Okay. Next, Andres Cano asked me to ask a question. So it's your turn now. Thanks.
Okay. Thank you. So thank you, Victor, for the very nice talk. I found it very, very instructive, and I think that you did a great job over the years on this system, so which I really appreciate.
Thanks.
So actually, I have a couple of questions. I don't know if I have the right to more than one, and maybe also a comment to Ilya's question on the role of the substrate. I think, in my opinion, or my feeling is that the thin films are needed because to grow these systems is really difficult. It's very, very hard to have samples with good quality, and it is only with thin films technique that you can get the right quality. So then I think that the interface with the substrate is special. It can have interesting physics itself, but for the superconductivity, I tend to think that it is really a bulk phenomenon here.
All right.
Do you agree?
Yeah, totally, yeah.
So my first question is about the 3-layer systems and actually the topotactic hydrogen that you probably know that has been suggested that, okay, in the infinite layer case, there is a difference between the lanthanum and the other systems. What is your, so I think that you have not considered that.
No.
Because, okay, the system is quite big, but what is your feeling in the case of the 3 layers? Do you think that they are more robust with respect to the topotactic?
Do you think about extracting hydrogen and getting it to fill to passivate, right?
Yeah, when you take the Radisson-Popper phase and you reduce it, there is the risk that the hydrogens will sit at the apical sites. Yeah. And do you have a feeling of?
Yeah, I mean, I don't know, because so we had here in Santiago some samples of the 438 of the powders, our colleague Fran Rivadulla here put them in the measured a few things of them, and one of the things he did was measuring EPR, and what we saw was that you had chunks, really big chunks of nickel metal. So the samples were terribly difficult to grow, and the microscopy of the samples was huge grains, and the quality was very poor at the time. So our conclusion was that you could have anything in there. They're so difficult to grow that you could have anything in there. And from a calculation point of view, starting to guess what dirt you would have in there, it was just a problem that was impossible to cope with. But certainly they are samples that are difficult to grow, very difficult to grow. So I saw that paper calculating that, and I said, yeah, okay, it could be. But I think that's a problem for experimentalists to actually characterize their samples well, and they should know much better than a theorist.
Do I have the right for a second question, Maria Jose?
Maybe there is another person waiting. He can ask first, and then you can go back and you can come back. Okay. Okay. So Frank, are you there? Yeah. You have to unmute yourself.
Hi, sorry. Okay. Yeah, sorry, Andres. Hi, Victor. This was a very nice talk. It's really nice to meet you. You're really a pioneer in this field, and I fully agree that it's an exciting field, and that these multi-layer nickelates are surely a way to go to investigate it further. So I have one question concerning your calculations for these single-layer compounds with the strontium doping. So from your results, you obtained that the low spin is a stable one with strontium doping from the LDL+2. So what is then your picture on this weakly insulating phase that appears with higher strontium doping? So what would be the picture that comes out from your calculations on this?
Yeah, I don't know. We don't even know where to start from. I mean, we don't know what could be the origin of that. We don't even have an idea of what kind of calculation one could do to, because there's so many possibilities that it's just disorder, localization, that would be beyond our calculation. So we don't really see anything. I mean, all these systems have charge density waves. I mean, one would need more data to actually understand that. At this point, I have no clue of what that phase could be. I mean, this, as we were saying before, if you had really clean samples and beautiful samples, then you could start guessing. But being so difficult to grow as they are, the first thing that comes to your mind is that you have dirt, you have disorder, you have localization, but we need more data. No, I just don't know it. So far we couldn't even guess.
Okay, thanks. Yeah, thank you.
Okay, so we can have the last question by Andres.
Okay, good. So actually, it's a question to Victor and maybe also to Frank and actually to the audience. So what do you think about the 4F electrons? I know that we don't like them very much because because we don't know how to treat them properly in these calculations.
Yeah.
Do you think that they play a role in the superconductivity of the nickelate, or on the contrary, for example, for the lanthanum, where there are no.
No, my view is that no at all. No, they don't play a role. That's my view. What we see is that the rare earth states, as you dope, they move away from the Fermi level.
Yes.
And they go away, basically. That's our idea, and you recover Cooperet-like physics. And that's what brings about superconductivity. That's our view. What's the problem for us is that we cannot treat them properly. So so people can you can tell me what, well, if you could treat them properly, you could make a prediction and actually say, hey, this is what is happening. Well, but unfortunately we cannot do it. And our idea is that, okay, if you see that all the ingredients that you put together are bringing the system closer to the electronic structure of the cuprates. And one additional ingredient you see is that as you dope, those states go away, go farther away, and start playing a less role. Then what comes to my mind is saying that they don't play a role. But I couldn't say they don't play a role because of this calculation that I did that treats them properly and says this and that. No, I cannot do that.
I also agree with that, and not only doping but also correlations. I think that they tend to move away the 4f electrons. This is what we saw.
Okay.
We treat correlations within the GW approximation.
All right.
We see that, okay, we did it for lanthanum, not for the other rare earth. In the case of lanthanum, they go away. The price to pay is that also the oxygen levels, they go down. But okay, regarding the 4f electrons, I tend to agree with you that probably they don't play a key role here. Okay.
Yeah, well, but that is pretty good. I mean, about the oxygen P, maybe that will help us understand what the actual role of the oxygen P bands is in the cuprates. If we find more systems here with a different charge transfer energy that are also superconductors, maybe that will help us understand what the actual role of the charge transfer energy is, even in the cuprates. So there are many reasons why these nickelates are interesting, not only for themselves, but for comparing with other systems as well.
I totally agree with you.
Yeah, maybe. Sorry, just I could maybe add, or maybe adding on this F electron issue. I fully agree with the both of you. Of course, also I'm happy if it would be true, because treating them is very difficult, as we all know. But I think there's also maybe a physical argument that we have this praseodymium compound, which is also superconducting, and the praseodymium and the neodymium F ions should behave a bit differently because of some Kramers physics. One is F2, one is F3. But since we see that they behave more or less identical, both compounds, then I would think that the influence of F electrons is really very minor on the physics.
Yeah, that makes sense.
Okay, well, thank you so much. The discussion is great as well, but I think we have to wrap up. You can stay after we close and talk in private. So, I mean, everyone is invited to stay longer, but I want to finish now. And just remind you of the talk next week, that we will have Jesper Nygaard from University of Copenhagen, and he will talk about hybrid nanowires, dots, and bound states as elements for quantum devices. So we hope to see you again.